Jessamine.
Okay, so got basically two topics left in chapter 19. Okay, so we're going to cover those today. Okay, the first one is something called the Hoffman elimination. Okay. So before we investigate that, let's do a quick review of what an elimination reaction is. Okay. Remember we covered that in 241, but you may have forgotten that. Okay, let's look at a setup like this here, where we have a leaving group on this carbon. And the carbon next door has that hydrogen. Remember we called that what? A beta hydrogen. And remember that that beta hydrogen had some acidic character to it. Okay. So if it is somewhat acidic, it can react with what? A base. So let's just react this with whatever the base is, but we do know it would have a lone pair on it. And so if you recall the mechanism, the base attacks the beta hydrogen. These electrons flow toward the leaving group, and the leaving group leaves. So as a result of this, we end up forming a carbon-carbon double bond. So this is a review of an elimination reaction. This particular mechanism, you might recall, was the E2 mechanism, where everything happened at once. Okay? So in elimination, we form a carbon-carbon double bond, or an alkene. Okay? This is what we're going to look at today. Okay? What's going to make this special is that we're going to look at a special leaving group, a new leaving group for us that we haven't considered before. Okay? And that new leaving group will make this called the Hoffman elimination. Okay? So any questions on a review of elimination reactions? Does that look familiar to you? All right. Well, with that in mind, let's get to the Hoffman reaction. Okay. So let's suppose we had this molecule here, this amine, this primary amine, okay? And suppose we wanted to react it with 3 of those. Does that reaction sound familiar from last time? What do we call that reaction? The exhaustive alkylation. Okay. So what kind of end product would you get there? How would you describe it? You'd end up getting 3 CH3s where? On the nitrogen. Okay. So I won't take you through that mechanism. You can look at the video from last time if you missed it. But here, that adds on 3 times. Let me just draw out the whole molecule. So that nitrogen ends up getting all 3 of those methyl groups. Okay. Cell phones have got to be put away. Okay, so everybody remember that reaction there. Okay. Well, what we didn't discuss last time is this nitrogen group with the positive charge is actually a very good leaving group. Okay? See, nitrogen has a positive charge. It would like to leave so that the nitrogen becomes neutral, and it's very happy that way. Okay? So this is what the Hoffman elimination is where we convert the amine to this alkylated amine, this ammonium salt, that makes this thing a good leaving group. Okay? And so if you look, we have 2 sides to where the leaving group is. So we have what? 2 sets of what? Beta hydrogens. Okay? So we got beta hydrogens here, that maybe we'll call these A, and beta hydrogens here, that we'll call B. Okay? So if I bring in a base now, okay, that base can now attack either B's or the A's. Okay? Let's look at both possibilities. So now I'll erase so I can go this way. And let's draw both products of A and B. Okay? So if the base attacks A, the double bond will what? Form right here. To give us that alkene. If the base attacks the B hydrogen, the double bond would form here. And so we would get that alkene. Okay? Do we have any questions on how those products form? Okay, so just mechanism-wise, if it was attacking a B hydrogen, you would have this kind of mechanism. Attack, double bond forms here, leaving group leaves. So here we get 2 different products. Remember, in organic, if we have 2 different products, what do we always ask? Which one is the major product? Which one is the minor product? Okay. Well, we want to figure that out. If you remember Zaitse's rule from 241, which of these two was the more stable double bond? This one or the bottom? Okay, this double bond here is what? A di-substituted double bond. This one down here is a mono-substituted double bond. So which of these two double bonds is more stable? The one that has more alkyl groups, okay? So the di is. So the A product would be the more stable, or what we call the Zaitse's product, okay? And so normally, this would be the major product because it's more stable, okay? Things head towards stability. But not so in this reaction. It turns out that the less substituted is the major. Okay? That the non-Zaitsev product is the major product. Why would that be? Why is it going against stability? Where this is less stable, but yet it's the major product. Any ideas? You have to come back and look on this side over here. Does that help? What kind of leaving group would you call this? What kind of leaving group would you call this? Starts with a B. A bulky. So you got a big, bulky leaving group. So when you think of bulkiness, what word comes to mind? Sterics. So this thing is going to cause steric hindrance, and so make these A hydrogens harder to attack than the ones on the end, the B hydrogens. Okay? So the B hydrogen is easier to attack. And since it's easier to attack, that will make the B product the major product, even though it's the less stable product. Okay? So what is determining the major product? It's not thermodynamics, it's what? Kinetics. Okay? So the easier that can happen, we're talking about kinetics. When we're talking about stability, we're talking about thermodynamics. Okay? So any questions on the Hoffman elimination? Okay, so two big things to take away from it. One is this new leaving group that we've learned. Okay? And then two, since it's a bulky leaving group, the major product is the less stable double bond, or the least substituted double bond. Okay? Any questions on that? Okay. All right, well, that's the Hoffman elimination. Now let's go on to the last topic here. And that's the topic of what's called diazonium salts. Diazonium salts. So, something new for us. Okay. What are diazonium salts? Well, let's take a look at a new reaction that I hope you're keeping track of. Okay, so here is a primary amine that this whole chapter's been full of. This time what we're going to do is react this primary amine with something new. We're going to react it with a mixture of sodium nitrite, okay, that's not nitrate, trait's O3, nitrite, ITE, and HCl. Okay, what in the world does this do? Well, it's going to transform, it's going to oxidize this NH2 into this thing here, where we get an N triple bond N. Okay, so no, nitrogen again has 4 bonds, so it's positive. Then you got the anion, and this combination is what's called a diazonium salt. Okay, that's what we want to look at. What special properties does this diazonium salt have? Okay. Well, let's do an example of this reaction here. Let's suppose we had cyclohexylamine or aminocyclohexane and react with the same reagents. Okay, so we know that will convert the NH2 to the diazonium salt. Give us that there. So what special property does that diazonium salt have? Okay. Well, again, I have a nitrogen with a positive. What did the nitrogen with a positive have last time as a special property? It was what? It was what? A good leaving group. That's what this thing here is going to be. Okay. So this thing here is a good leaving group. Okay? So when I react this with a nucleophile, this N triple bond N comes off as a leaving group. All it is nitrogen gas. Nitrogen gas is very stable, isn't it? So that's a weak conjugate base. Remember, weak conjugate bases are very good leaving groups. So the same thing down here. If I brought in a nucleophile, such as the methoxy ion, it can come in and substitute. And give off nitrogen gas. Okay, so it invites a way to do very easy substitution reactions. Any questions on that? So see how the Hoffman and diazonium salts kind of have similar properties? Okay. Let's look at diazonium salts from another angle. This time, let's look on benzene. Okay. Remember how to put an NH2 group on benzene? What do you have to put on there first? The nitro group. Very good. So let's do that little review here. So nitric acid and sulfuric acid. So that puts on the nitro group. Does anybody remember how to convert that to the NH2? Okay, very good. Have some good memories there. Zinc and HCl. Okay. So NH2 had to be put on in a couple of steps. To give you this, remember it was called aniline. Okay. Or technically, you could call that what? Phenylamine, okay? Or technically, you could call that aminobenzene, okay? But now we have the NH2 group on there. What could we convert the NH2 group to? A diazonium salt. Using what? The same reagents. Okay, so let's do that. So, what did I use? I forget.
Sodium nitrite.
Sodium nitrite and HCl. Okay. So we get our diazonium salt. Well, at this point, what do you think we can do now? Got a good leaving group, so we can do what? A bunch of substitution reactions. So I could bring in a whole bunch of what? Different nucleophiles. That's what we're going to give you. And these are all on page 912. Okay? So let me put them on the board for you. Okay, so here's all the ones you want to be familiar with. These are all easy to remember. What do you think the top one will put on the ring? An OH group, make phenol. Okay, so you see the oxygen there. Okay, again, we won't go through the mechanism. What do you think this one will put on?
Chloride.
Chloride. How about the next one? Bromine. How about the next one?
Cyanide.
CN, make benzonitrile. How about the next one? One atom. The fluorine. How about the next one? Iodine. And the last one's a little tricky. You got 3 atoms to choose from. What do you think will go on that one? Gotta be one atom. Got one left. Didn't everybody say? The hydrogen. Okay, so you just get benzene back. Okay. So those are the reactions that you want to remember. Okay? So here you have another way to make phenol. Some extra ways to make chlorobenzene and bromobenzene. Okay, benzonitrile, we really didn't learn how to make that one. And then these down here. Okay. So what I want you to do now for the next several minutes is put all these reactions on your note cards. If you don't have any note cards here, we can do one of two things. Either borrow some from a friend, or take out a clean sheet of paper and put them all on the same sheet. Okay? So you have 2 sets of reactions to put on there. You got the Hoffman that we did earlier, and you got these diazonium salts. Okay? So I'm giving you free time to do it in here, to give you a study tool. Because in the next exam, you're going to have a lot of reactions. You got the aldehydes and ketones. You got the amines, okay? Put them on your paper now, okay? Put them all down now so it's summarized, so your mind sees them all, so you don't have to turn pages to see them. They're all right there. Your mind learns easiest when you make it easy for it. When you make it complicated, the mind gets complicated. And you forget.
For the Hoffman elimination, you just want us to, for our final product, you just want us to have the major product? You don't want us to do both of them?
Yeah, do
Just
both
do
of them and
both
say
of them.
which is major, which is minor. If you have any questions on what to do, just call me over. give you directions. Monday, we're going to start a new section, so I want you to get this capped off so you can study appropriately over the weekend. That's right. Right, right. So each of these reacting to that. Okay, so I hope you understood that. Each of these is reacting with this thing here to form each of these. And what I put on the board here was using some principles that we learned in the chapter. Okay, so if you want to follow along up here. Okay, so my goal was to start with benzene, and I wanted to make this meta product here. Okay, so just follow me here. So I put on the nitro, then convert to NH2. Okay, and then I'm going to block that amine by putting on an acyl group, make that a mid-linkage. I can always convert it back through deacylation to get it back. But I'll use this to put on another nitro and convert it to NH2, so that now only this NH2 converts to the diazonium salt, and then a substitution reaction with the CN puts that on, and then I can deacylate and get that thing back there. Okay? So I'm just showing you the power of that blocking group when I acylate, so I can continue to do other chemistry on there. Okay? So if you want to write that down, just to show you how you can block one amine group and why that might be helpful. Stop here for today. Get this down as you finish. And then if you want to pick up any quizzes that you have up here, feel free to.